In our previous tutorial, we implemented a simple linear programming formulation in CPLEX OPL, which was this model file. And basically, in this linear programming formulation and implementation, we have written it in an open form. But especially if we have a large number of decision variables, we need to write the model in a compact form, because otherwise writing the model will take a lot of time. Assume there are 100 decision variables. Then, as you see, we defined our decision variables like this. So if we have 100 decision variables, then you need to define 100 decision variables one by one. And for example, in the objective function, it is just a multiplication of each decision variable with a coefficient and summing them up. And if you have 100 decision variables, then you need to write many terms on this line. And it is not practical. For this reason, we need to write the model in compact form, and CPLEX, one of the powers of this CPLEX OPL is it allows you to write the model in a compact form, and it's pretty easy. But you need to understand the idea. So in this tutorial, basically, we are going to implement a model in compact form. First of all, let's have a look at this example problem. Let's formulate it, and then we will implement it in CPLEX OPL. In this example, basically, we have a production facility which can produce 10 different products. So all the necessary information about the products are given in this table. We have 10 products. From each one of these products, by selling them, we can obtain a profit of this much. And each product consumes a time in our manufacturing facility. For example, if you produce one of product 1, it takes 5 hours. If you produce 2 product 1s, then it will take 2 times 5. Okay? And in total, there are available 200 hours of production time in our manufacturing facility. Similarly, the total material requirement of each of these products are given in this column. First product requires, if you produce one of type 1, product type 1, then you need to produce 21, let's say, kilograms. Let's say this is kilograms of material. And the total available material is, let me change it to kilograms, 5,000 kilograms. Okay? And on the other hand, we also have the demand restrictions. It means that in 1 week we can sell at most 218 of product 1, 589 product 2. So these are the restrictions on the demand. And finally, there is another restriction over here which says that the total number of product 1 and 5, the sum of these, product 1 and 5, cannot be more than the number of product 6. And the question is to formulate this problem which decides on the product mix, and our objective is to maximize the profit. First, let's formulate this quickly. I will not spend too much time on the formulation, and let's implement it in CPLEX OPL. Okay, first thing is to decide our decision variable, and this is a simple model, in fact, and our decision variable will be X. So, for example, we are deciding on how much or how many product 1s we are going to produce, how many product 2, and etc. Okay, so you can say x1 denotes the number of product 1, x2 denotes the number of product 2, and you need to do this up to x10. But in compact form, we can just say that xi is the number of product I produced. And this I goes from 1 up to 10. This is our decision variable definition, and let's write our objective, and the objective is in fact easy. We want to maximize the total profit, and the total profit is basically this. For the first product, if you produce 1 from first product, then the profit is $8. Then you will multiply with the number of product ones that we produce. Again, multiply the second profit with the number of products and etc. So this is 8x1 plus 7x2 plus 5x3. You see, writing this all up to 6 times x10, and it is not practical. For this reason, we convert this into compact form, and since this is basically a summation, we use the sigma notation, the summation notation. And how many terms do we have? This is term 1, this is term 2. How many terms we are summing up? Basically 10. So we say that our summation index I takes values from 1 to 10. I goes from 1 to 10. And what do? We multiply each one of these xi's with a coefficient, okay? And then it means that we need to write this as a parameter. So if this is our model, LP model, then what do we input into this model? We input the number of products, right? Number of products, which is 10 for our example. What else? We input the profit values. And for these profit values, basically this is just 10. But what is the profit? So it is different for each product. So it is not just a single number, but it is a vector of numbers. Then I need to define these numbers using a parameter. So let me write here parameters of the problem. And for profit, I'm going to use this PI. Profit, or let me write unit profit. Unit profit from product I. Okay, so it means that P1 is equal to 8, P2 is equal to 7, and P10 is equal to 6. Basically, my objective function in compact form is Pi times Xi. We are trying to maximize this. And subject to, it says that there is a total available time in our facility is 200 hours, and the time for each producing each product is different from each other. So what do we have as a constraint? We multiply the time of product 1 with x1, product 2 with x2, and etc. up to x10, and this will be our total time. Let me write it here, and I will clean it later on. Plus 2x2 plus up to 3 times x10, and this should be less than or equal to our available hours, which is 200. And again, this side can be written in compact form as I from 1 to 10. Again, we are multiplying this xi with some coefficients, but these coefficients are different than the coefficients in our objective function. Okay, so it means that I need to define a different parameter. As you see, another input of our model is the time. Okay, and let's say that these time values are denoted by TI, unit production time, time of product I, let's say. And in this case, we basically multiply this xi's with ti, and it should be less than or equal to available hours, which is 200. By the way, I am inputting this available hours also into the model. It's also a parameter. Okay, so how do we write it? We write it I from 1 to 10 ti times xi less than or equal to 200. Okay, the material requirement is very similar to this one, therefore I'm not explaining it in detail, but I need to define this mi as the unit material requirement of product I, and it means that I from 1 to 10, this mi times xi should be less than or equal to available amount of material. So what else we input into our model? The material requirement and available materials. Okay, and what else? We have these demand restrictions. And what are these demand restrictions? Be careful, sometimes the students or some friends do not pay attention, and basically they say, okay, the demand restriction is something like this: 218 times x1 plus 589 times x2 up to 336 times x10 should be less than or equal to or greater than or equal to something. But in fact, the demand restriction is not this one. The demand restriction says that the number of x1 that you are producing cannot be greater than 218. The number of x2 cannot be greater than 589. The number of x3 cannot be greater than or equal to this one. So it is not the summation. Okay, we need to write each one of these decision variables up to x10 less than or equal to 336 one by one. And in order to write this in compact form, basically you see there's no summation on the left hand side. There's only this decision variable xi. And on the right hand side, what do we have? We have different numbers. So we are going to represent those different numbers as di, which is the demand of product I. Basically this is weekly demand, and you can say xi is less than or equal to di, but I need to say that I am writing how many constraints? 1, 2, 3. I'm writing 10 such constraints. And in order to denote that there are 10 such constraints, I need to write it here, I from 1 up to 10. Okay, so this is the compact form of writing these type of constraints. And again, what else do we input into our model? Demand values. And finally, we have this restriction over here which says that product 1 and 5 cannot be more than the number of product 6, and it is basically x1 plus x5 less than or equal to x6. And for all decision variables are greater than or equal to 0, I from 1 up to 10 again. Okay, so this is our model in compact form. Now we are going to implement this in CPLEX OPL, and let's do it. Let's see how can we do it. For this purpose, I'm going to open just a new project. As you see, my previous project is here. Okay, so I'm going to now open a new project from File to OPL project, and I will give a name to this project. This will be, let's say, LP in compact form. Okay, so this will be the name. If you like, you can change the location and folder. And for this project, I am going to create a model file. I will not use a data file. I will just use a model file, and I will add a default run configuration. Okay, if you don't click on these, you can add these later on, as I explained before. Just click on finish, and as you see, this LP in compact form is opened. You see, it's this one, and there is a model file on it, and there is a run configuration for which the model file is already copied inside. Okay, now we are going to write this model, our model, into here. But okay, in our previous model, we only defined our decision variables. You see here. But in this case, in this model, I have decision variables as well as I have these parameters over here. So it means that I need to define these parameters as well. By the way, the output of our model, what is the output of our model? Let me write it. It is the values of xi, right? The decision variables. Okay, so let's start defining the parameters of the model now. And the first parameter that I'm going to define is this, unit profit. Okay, so basically I will just define it, but when you define a parameter, it can have two types. It can either be a float or integer type. Okay, and the keywords to define these parameters are float or int. Float means the numbers, this number, I mean the value of the parameter can be a fraction. It doesn't need necessarily be an integer. It can take 5.2 for example. But if it is integer, it means that it should only assume integer values, positive or negative integer values. For my case, if you look at this table over here, all the profit values in this column are integers. So I can define my parameter as an integer, but if you define it as a float, again you will not receive an error message. It is not a mistake to define it, but if you already know that this is integer, you can define it. And as you see in the definition of the parameters, we just start with int. Okay, int, and there is no sign restriction on the parameter like the decision variable. In the decision variables, we need to define, if it's a non-negative integer, we need to write it int plus. But here we don't write it for the parameters, and then write the name that you want to give to this parameter. I will give p. If it is just a single number, then it's all. But as you see, this p value, the profit value, is not a single parameter. It is a vector of parameters, okay, or array you can say. And for that reason, in order to define such a parameter, we use these brackets. And now inside the brackets, I need to say how many numbers we have in this parameter. And as you see, we have 1, 2, 3, 4, up to 10. Therefore, I define this parameter as 1 up to 10. This is the syntax, okay? 1, 2 dots, and then 10. So it will take 10 different values. And now, okay, you can just finish this definition, in this way. But what happened? This is a parameter. It means that you know their values. And what are the values? The values are given in this table. But as you see here, we haven't assigned any values to these parameters. Okay, so first I will show you how to make these assignments directly in this model file, and in the following tutorials I will show you how to use an additional data file and how to read this data from an Excel file. Okay, now let me define these parameters. Since I am going to define 10, the syntax is this. Okay, again we write equal to, and within curly brackets we start writing these values. Okay, let me try if I can copy these values from here to this CPLEX, otherwise I will write it by hand. Okay, I copied them. The first one is 8, the second one is 7, but we separate them with a comma. Okay, then the third one is 5, the fifth one, okay, let's just format all of them. And each line must finish with and must end with a semicolon. You see, we define 10 values for P1 up to 10. It means that P1 is equal to 8, P7 is 7, P2 is 7, P3 is 5, and etc. And now you can just use this number, this value P1, so that it will understand the value of P1 is equal to 8. Okay, so this is how we refer to this parameter. Similar to this, I need to define other parameters, Ti, Mi, and Di. So let's define this Ti. I am going to copy these parameters to here. Again, all of them are integers, so I will say this is T. You see, I'm not writing the index I. I'm just writing T, and it takes values 1 up to 10, and these values are equal to these numbers over here. Again, let's format these. Okay, I just copied all the data from here and written in the same format to here. So these are our parameters. Now I'm going to define our decision variables. And if you look at our model, we have only a single decision variable, which is xi. And the definition of a decision variable and the parameter is slightly different. Again, we need to use this type, whether it is float or integer, but also we need to define if this is a decision variable or not. So if we are defining a decision variable, we should start with this keyword, the var, first. Then we need to write its type, and in linear programming, all decision variables should be float. And if a decision variable is non-negative, meaning that greater than or equal to 0, we need to write it as float positive. Okay, then the name of our decision variable, which is x, you see I'm not writing x1, x2 now, it is just x, not xi, it is x. And then I write it the values that this x can take, and in total I have 10 different x values. So this is x1 up to 10, and I'm going to write, of course you don't need to set this anything because it's the output of the model, and you just end the line with this semicolon. Okay, that's all. Then we are ready to write our model, and since it's a maximization model, I'm writing maximize. And now I'm going to write this in compact form. Okay, so I need to use this I from 1 to 10. So the keyword for summation is sum. Okay, as you write sum, it turns into blue. It means that CPLEX understands it. And then, as you see, for this sum, I need to mention from where to where, summation of which index and where to where. So I will say that summation is will use this I index, and it will go from 1 to 10. Okay, so again the syntax is writing this inside this parentheses, and I am saying I in 1 up to 10. Again, this in, as you see, it turned into blue, it's a keyword. It is the index that I am using, and I don't need to define it anywhere. This part is the definition, and this 1 up to 10 says the limits of this summation. And then I need to write the summation part, which is pi times xi, and the syntax for this is p. If you see, we defined it here, p, and we need to use these brackets pi. Then the multiplication sign is this asterisk. Don't forget it. You need to write it, otherwise it will give you an error message. Then pi times xi. Okay, and with a semicolon. You see, if I forget this asterisk, if I don't write it, we got an error message, and if you look at this error message, it says that there's a syntax error. Okay, so it's basically because you forgot this asterisk. And you see, this is, again, you can leave as many empty space here as you like. It's not a problem for CPLEX OPL. Since this is a multiplication, you don't need to write it inside such a parenthesis, but also it's also possible to write the term that you are summing inside such a parenthesis, and it will not give you an error message. and for example, if inside this parenthesis you have this minus 10, for example, writing this in this way and in this way is totally different. Okay, so you need to be careful whether you are summing this. Let me give an example here. I from 1 to 10 pi times xi minus 10, if you are summing this, or if you are summing pi times xi and just subtracting 10 only one time. These are two different things, so you need to be careful with what you are writing. So therefore sometimes you may need to use these parentheses. In this case, as I said, you don't need to do because it's just a multiplication. And this is our objective function. And what about the constraints? To write the constraints, we write subject to, and we write all the constraints within these curly brackets. First constraint is this one. Okay, on the left hand side I have this summation again, therefore I use this sum and then I in 1 up to 10. Okay, then what am I summing up here? It is ti times xi. So since I define this ti and xi, I can use basically, okay, these definitions, these notations, ti times xi. But assume you want to use here yi. Okay, so if we just use y, by the way, let me write the constraint. The right hand side of the constraint says that less than or equal to 200. So less than or equal to is written in this way, in this way, less than or equal to 200. Now this is the constraint, and if you write, for example, y here, you get an error message and it says that y does not exist. Why? Because you forgot to define it. Okay, so it should be x. And on the other hand, you see this is ti times xi. Let's assume that I am multiplying ti with xj. Again, there is an error message and it says that name j does not exist. Because you see inside this summation I have I in 1 up to 10, and then where is this j? What's the value of j? Okay, it's missing. So it should be, for this example, it should be I. We will make later on we will make other examples in which we have both xij, and we will define I and j separately in those cases. And this is the first constraint. But you see on the right hand side here we have this number 200, which is the available manufacturing time. And for this, again, what you can do is you can define this int and another parameter. I will say available time, okay. You can define these parameters like these sentences. You don't need to just say A, B, M. In CPLEX you can also write these words. Okay, so I will define this avail time and I will set its value equal to 200. Okay, it is just a single value. By the way, look, when I forget this semicolon here, the error message appears one line below and it says that syntax error, unexpected decision variable, and etc. And you should, when you get such an error message, you should look at both to this line if there is a mistake here, and also the previous line. And in this case the mistake is here, and when you just put this semicolon you get rid of that mistake. And now when I define this avail time as 200, then I can copy and paste it to here. So I don't use this number inside the model, but I define it as another parameter. As you see in this model, available time is also an input into my model. It's also a parameter. Now let's write the next constraint, which is the material constraint, and it is very similar to the first one. For that reason, I will just copy and paste this constraint here, and I will just change it. So again, it is I from 1 to 10 multiplication of mi. So this t should be mi times xi, and it should be less than or equal to 5000. And again, like this available time, I can define another parameter, okay, which will be available material. I will just write available mat, and its value is 5000, and we can copy it to here, and it's perfectly fine. And look, here there's only one single constraint. Here there's only single constraint, and again this is just one constraint and this is just another constraint. I have written just two constraints here. Now let's go to the next one, which is xi less than or equal to di, and you see I from 1 to 10. Now this is a different type of constraints. Here I have just a single constraint, but here I have 10 different constraints. Okay, then how do we write these 10 different constraints? Again, there is a keyword for this one, and that keyword is for all. Okay, what does for all means? Sometimes instead of writing this I from 1 up to 10, we simply write it as this symbol, and this symbol means for all possible values of I. Okay, therefore we are using for all statement, and the syntax is similar to this sum statement, for all, but for all what? For all I. And what values this I takes? 1 up to 10. Okay, so what do we do? Inside this for all, again I write I in 1 up to 10. Okay, and then what's the constraint? The constraint is xi on the left hand side, so I just write xi, and then less than or equal to, and on the right hand side I have di, and I already defined that di, so di, and this is the constraint, and this constraint is in fact 10 different constraints. Not, although you see a single line, there are 10 constraints here: x1 less than or equal to d1, x2 less than or equal to d2, and etc. And another thing here is, if you like, you can write this constraint in this way also. So you write this for all in one line, and then you write xi less than or equal to di in the next line, and it's perfectly fine. No problem with it in CPLEX OPL. And again, if you can leave as many empty spaces as you like in CPLEX OPL. Okay, let's complete our model. Another constraint, this constraint is x1 plus x5 is less than or equal to x6. Okay, now how do I write it? So sometimes some of our friends try to write it like this: x1 plus x5 less than or equal to x6. And when you do it, you see we got a mistake, we got an error message. It says that x1 does not exist because we defined x in this way, and when we want to refer to this element, the first element of this x, which is a vector, I need to write it in brackets. Okay, so it should be x1, and you see when I correct it, now there's another message. It says that x5 does not exist. So usually CPLEX finds the first mistake and then gives you the message for the first mistake. When you correct it, then it finds the next one. So it means that whenever there are a number of error messages here, look at the first one, resolve the first one, and then maybe all others will be resolved by itself. And the x5 will be referred in this way, and x6 will be referred in this way. Okay, now we have all these constraints, and you see there is another constraint, xi greater than or equal to 0, and for all I again. And basically what you can do is you can write something similar. By the way, for this constraint, as you see, there is no for all or there is no sum. It is just x1 plus x5 less than or equal to 6, x6. So for all I in 1 up to 10. And what do? I said, say xi greater than or equal to 0. Okay, this is the non-negativity constraints. But you don't need to write this. Never write these sign restrictions, because the sign restriction is here. Okay, we define it here. We say these x variables are float positive. This positive here is the non-negativity restriction. If you delete it, okay, and if you don't have this constraint over here, then it means that this x variable is unrestricted. It can assume negative values. But when you have here, it means that you already have this constraint and you don't need to write this constraint. Don't write it. Define it here. So this is the model, and let's solve this model. How do we do it? Go to this model file, the run configuration, right click on it and click run this. And when you run, if everything is correct, if there is no mistakes with the model, it will give you the solution. And you can see the solution from here. As you see, all decision variables are 0, but the second one is 100. Okay, and you can see the x variable value and the objective function value here. By the way, you see it says the solution is optimal with objective function value 800, and the x value, when you go on top of this, there appears small button here. When you click on it, you see the value of these x. The others, reduce cost and sensitivity range, we haven't learned it yet. If you know sensitivity analysis and duality, you will understand what's going on here, but you don't need to look at that part. This part is important for you. This is the solution. And since we define these parameters as vectors like this, if you want to check if CPLEX read them correctly, you can have a look at these parameters. Okay, available material is 5000, as you see here. Available time is 200, as you can see here. And the demand value, when you click on it, you will see each one of these demands or material requirements for each product and etc. And you can check if all of these are correct as given in this table. Okay, so this is how we write a model in compact form. The last thing that I want to talk about in this model is this. If you look at this model, we see that everywhere we have written this statement 1 to 10, 1 to 10, 1 to 10, and inside the model here sum in 1 to 10, or for all I in 1 to 10. Okay, and writing this all the time may not be practical. You may ask, is there a simple way to do it? Or instead of having 10 products, I may have just 5 products. Okay, just delete the first next 5. Now you see this is another problem. And how do I solve this problem here? What should I change in this model? Let's solve it. So for this reason, I'm going to create a new model file, and I will say LP in compact form with 5, let's say, variables. Sorry, I will just say it to here. 5 products. This is the name of my model file. And for this one, I'm going to create a new run configuration. Again, the name will be configuration 5 variables. Okay, finish it. And in order to have this run configuration, I need to move the model file into this run configuration. You see it's now inside it, and it's currently empty. And if you look at this model now, what do we have? The decision variable definition, is it changed? No, it's the same. It goes from 1 this time it goes from 1 to 5, but the meaning is the same. What about the objective function? It is the same, but it goes up to the 5th product. And what about the other constraints and etc.? They don't change, only since now we have let's say 5 products, maybe this constraint over here is invalid now. You can just delete it. Or if the constraint says this is up to, let's say, x3, then it's the same for both models also. So let me change that in the original model also, x1 plus x5 less than or equal to x3. Now what can I do? I can just copy this model from here to this new one, because the model is the same. But the thing is, what is changed? Now I have 5 products, so I need 5 data for that one. Again, for this second, I'm just deleting the last 5. Okay. Again, delete this last 5 and delete this last 5. And everything is the same. All other are the same. But what also I need to change? I need to change this from 1 up to 5. And also this one, I need to change it 1 up to 5. And this one, 1 up to 5. So you see, everywhere I need to make that change. And you may ask, is there an easy way to do it? And yes, there is. And how can you do it? We can just define a parameter to denote the number of products. Okay? So int, you can say it's just n to denote the number of products, or you can just say n products. Okay, this denotes the number of products. And how many products do I have in this case? It's just 5, right? So when I define it, I can go to my model and I can just say that it goes from n 1 up to n products. Okay, and this one also up to n products. This one, I change all these in my model from 1 up to n products. This one, this one, and this one, and that's it, I guess. So in this new model, it's more practical. Why? Because if instead of 5 I need to solve a model with, let's say, 20 products, I just change this to 20, and in all of these it automatically changes to 20. You see, all of them change to 20. I just need to write all the parameter values for this 20 into these definitions. Otherwise, I don't need to change anything inside my model. Okay, this is a practical way to do it. So last thing is this. Instead, again, repeating the same thing again and again and again, here is not practical. In order to do it in an easier way or more effectively, what we can do is we can define a range. Again, this range is a keyword in CPLEX, and we can give a name to this range, and that name is products. Okay, you see, this is number of products, which is currently in the current example 5, and I define a range which is in fact equal to this 1 up to n products. Okay, basically the syntax is this range of products goes from 1 up to n products. You can also define it, if you like, 1 to 5 here, or you can define it 1 up to n products in this way here. Then when you do it, inside each one of these you just use up to products. Okay, because 1 up to n products has a special name now, which is products. Okay, again here it is products, here it is products, and then here it is just products and products. Okay, now you see it is much more easier, much more efficient, and when you want to solve an example with, let's say, even 100 products, you just change this number over here and you enter the values here and you solve it. Okay, you don't need to change any other thing. Of course, the previous version was not wrong, but if you want to solve the same example with different numbers, then you need to make a lot of changes. But if you write it in this way, it will be much easier for you to solve it. Now let's solve this problem with 5 products. Okay, in order to do it, right click on this and click run this, and you will obtain a result. Let's wait for the result. You see the objective function is still 700 and the decision variable values are these. And now let's assume that we have a more available time and available material is increased to 10-folds. Then what happens to the solution? Right click on this and click run this, and you see now we have a different number. And if you look at the x values, you see now x1, x2 and x3 values are given in this way. And of course these x values were defined as float. Okay, here we define them as float because this is linear programming, and since they are float, the solution may include such numbers, I mean fractional numbers. Now let me show you another common mistake that you can do. Let's assume that the profit from the second product is 7.5. Okay, now when you write it as 7.5, you see there is an error message over here, and when you look at these problems, it says that cannot use type float for int. So what does it mean? It means that there is a fractional value here, but you define that parameter as an integer. Integer cannot assume fractional values. In that case, you need to define this parameter as float. If some values of the parameter can take fractional values, then you need to define it as float. And also, even if all of them are integers, but you are not sure if they might take float values, still you can define it as float and you will not receive any error messages. And when you run this model, you will obtain the correct optimal solution. Okay, so this is all about how to write a model in compact form. But in this version we have assigned all these parameter values from this model file, but this is not something that we like it. And in the next tutorial I will show you how to define your model in a compact form and then read the data from an additional file. Okay, so see you in the next tutorial.